This is Lecture 9, Example 3/32. Please make sure you read the question first. We have a slider A and B that are connected by a light rigid bar and moves with negligible friction in the slots, both of which lies in a horizontal plane. For the position shown, the hydraulic cylinder imparts a velocity and acceleration to a slider A of 0.4 meter per second and 2 meter per second square for the acceleration, both to the right. Determine the acceleration of slider B and the force in the bar at this instant. In this case, first of all, you want to realize, where are you observing this from? This is on a horizontal plane. So A and B, we're looking at this on top of it. Right? So if we're looking this way, we're looking on top of it. It's on the horizontal plane. You're looking on top of the horizontal plane. It's a top-down view. And they're both to the right. So when it slides, A will go this way and B will go this way. And they are all constrained within the channel. Therefore, we can define a positive direction. We'll say this direction would be our SB positive, and A, on the other hand, will go to the right horizontally. This is our SA positive direction. We were given velocity of A as 0.4 meter per second, and we have acceleration of A of 2 meter per second square. So it seems like A, all the information about A is given. And A and B are connected by this rigid bar. That means the distance between A and B will remain constant. And this will be the key to solve the question. We know A, and A is connected with B via this rigid bar. What's happening at B? In a situation like this, most likely you will be required to understand the geometry between them. So let's take a look. We have a rigid bar, have A, we have B. So naturally, we can form this triangle. So let me draw this triangle over it, and then I'll move it over. Here, here, and horizontally connecting to here. Now, I want to move this over to here. This is the B, this is A, and this is 0.5 meter. We'll call this the length L. So when B goes down, this will be our SB, and A will be this length, SA, sorry. Okay? Because we have 60 degrees here, that means here we would have 120 degrees. And because we also have a 30 degree here, that means this is 30. That means this is also 30 degrees. Therefore, we are looking at a equilateral triangle here. So there are several ways that you can solve this, or several ways to look at this. There's only one way to solve. Looking at the triangle, the geometry is given. So triangle, there are two methods or two tools you can use: sine law and cosine law. Especially now you know the longest side, SA and SB are equal. So you can find out the length of SA and SB via sine law. Through sine law, we have 0.5 over sine 120 degrees equals to, you can either use SA or SB, they are equivalent. over sine 30 degrees. Therefore, we have our SA equals to SB equals to 0.289 meter. Okay, that's the length here and here. They're equal. On the other side, on the other hand, the cosine law can give us the overall relationship between SA and SB because they are connected by this rigid bar. This 0.5 meter will remain the same all the time, no matter how A and B are changing, whether it's completely horizontal or completely in the tunnel where B is. Right? So through cosine law, let's see what this can give us. Cosine law, we have L squared equals to SA squared plus SB squared plus 2SA SB cosine 120 degrees. This angle here will remain the same, right? This is irrelevant to the movement of A and B. This is the angle the two channels are making between each other, 120 degrees. So we have a constant here, we have a constant here. And these are variables here. And essentially we only have two variables, variable SA, variable SB. This is repeating here. Now we have a length, the relationship between length. Remember the three basic variables in dynamics: displacement, velocity, and acceleration. The second two, velocity is a derivative of displacement is velocity, and then derivative of velocity is acceleration. Whenever you see a relationship come up like this, ds over dt is dv, or dv over dt is acceleration, should come to your mind. Okay, as that being said, let's take a look. For this cosine law, we have two variables here. Because we're given velocity of b, we want to find out what's going on with the velocity at a, and a and b has a length or displacement relationship. We can try to take the derivative, find out what's happening between VA and VB. Therefore, we'll take our first derivative here. I'll take the first derivative with respect to time. The total length L and, well, you can argue here this should be 0. Later on, I will cancel this out because the L dot is a constant. The derivative of constant is 0. But I'm just writing this out here. I'm taking a derivative with respect to time to all the variables here. Although L is not really a variable, but I'm now just treating this as a variable. What if it's a variable? SA squared will give me 2SA dot. For SB squared, 2SB dot. And then comes to this part, taking the derivative. Be very, very careful. Okay, you have two parts here, SA and SB. Essentially, this 2 cos 120 degrees is a constant. It's simply a SASB derivative. So we'll have minus 2 cos 120 degrees in the bracket. We have SA dot SB plus SA SB dot. Now, you should realize this is a velocity of A, and this is a velocity of B. Then we'll tidy up a little bit. Now we realize the L dot is a 0. So we have 0 on the left-hand side. On the right-hand side, we'll have 2SA VA. Okay, I'm changing this SA dot to VA plus 2SB VB plus VA SB plus SA and VB. Okay, in case you're wondering, this cos 120 degrees is -1. So now I'm just connecting all those, tidy up things. Okay, what do we have? We know our SA, we know VA, we know SB, we know VA, we know SB, we know SA. What's the variable here? The only unknown variable is our VB. Now we can sub in all the numbers here to get VB is negative 0.4 meter per second. We also need the acceleration of the piston B. Now we have the velocity. We can take the second derivative, or take the derivative again from this relationship. Then we know the derivative of VA and VB will give us the acceleration of A and the acceleration of B. So we'll take the derivative again. We'll call this second derivative. Okay, it's a second relative to this one. Okay, the first derivative gives you the velocity relationship. The second derivative will give you the acceleration relationship. Okay, on the left-hand side, 0 remain as 0. First part, 2SA dot VA plus 2SA VA dot. Okay, remember now you have two variables, both SA and VA, they are variables. Make sure you treat them as variables during the derivative. And then this part is 2SB dot VB plus 2SB VB dot. Okay, what do we have here? This is our acceleration of B. Okay, just be patient. This is not a very hard derivative. If this is in calculus course, you should be able to do this right away. Okay, just be careful and be patient. The next one is VASB part. We'll have, let me change my color back here. We have VA dot SB plus VASB dot. And again, you realize this is your acceleration of A. Okay, we still have one last component to deal with. The last one will give us, I'm running out of room here, SA dot VB plus SA VB dot. Okay, let me move this up, see if I don't have enough room. I'll just put it here. Okay, it's a very long equation. As long as you're being patient, you should get it right. You have many variables in here. Make sure you treat the variable as a variable. When you take the derivative, you need to multiply that variable again. Okay, now we can tidy up this equation. 0 to VA square plus 2SA AA. Okay, I'm just now all SA, this is VA, right? This is essentially VA. So VA is VA squared. That's how this VA square is calculated, being simplified to. Okay, the same thing applies to everything else. Okay, give it a try by yourself. VB squared plus 2SB AB plus AA SB VA VB plus VA, VB plus SA, AB. Okay, I tried to match the position for everything. For example, the last term, SA VB dot is the same as SA AB. SA dot is your VA. Okay, VB remain the same. SB dot is your VB. VA remain the same. Okay, etc. etc. These two whole equations are exactly the same. The lower one is a simplified version of the top one. Now let's re-examine this equation here. We know VA, we know SA, we know AA, we know VB, we know SB, we know AA, we know SB, we know VA, we know VB, VA, VB, we know that, we know SA. So this whole thing, the long equation, seems ugly, seems nasty. The only variable you have is this AB. And that's exactly what we want. Therefore, we've got AB is negative 2.37 meter per second square. This is our first answer here. We got the acceleration. Okay, let me circle this one as well. Okay, this is the interior number, right? This is the velocity of B and acceleration of B. Next, we need to find out the question is also asking the force in the bar at this instant. Okay, let's take a look what's going on here. Now, coming back, you can flip back to the first page where the question is. We want to draw the free body diagram. So for the B component, what force is on B? Okay, thinking about the GNEF method. Gravity is a must. There must be a gravity. But because this is a horizontal plane, gravity is pointing down and the normal force is pointing up. They will have to cancel out each other because I'm moving on the horizontal plane. Okay, I don't essentially need to draw out the gravity and the normal force because they are canceling each other and they are not in my way. They are perpendicular to my motion. And this is a smooth plane as well. So I don't need to worry about friction. If I have to worry about friction, then I have to worry about the normal force. So for B, essentially, let me draw a line here. Okay, so this is my this is where the channel is. Okay, let me draw this one here. Okay, this is where the channel is, and my B is right here. Okay, so this is my B. For B, essentially there's only one force acting on it, which is coming from the bar. Let's call this force T. And this force T is making a 30-degree angle with the channel that B is sliding. So therefore, if we define, let's define positive is pointing up, and we have sum of F equals to MAB, right? Then we have negative T cos 30 degrees equals to MB AB. Subbing the number here, MB is 3 and AB is 2.37 as we calculated from the previous page. And the negative sign is carried over from the previous page as well. Therefore, we've got T equals to 8.21 Newton in the bar. And this is the only force that B is experiencing. So that only force is contributing to this acceleration here. And I'm accelerating along this channel here. The B is not going here because the B is being restricted by the two walls. B is going this way. So you need to break the T into this here. So T is essentially T cos 30 this way and T sine 30. Right? And essentially there will be a normal force here, but any force that is perpendicular to the motion without consideration of friction is not affecting my motion at all. So this is my T here, the tension in the bar. Well, the bar is connecting A and B. That means this force will be the same acting on A as well. Same magnitude, but opposite direction. Okay? Now, if we look at the free body diagram of A. For the free body diagram of A is experiencing a force from the, whatever that's called, the piston. Yeah. I didn't specify the name. So we'll call this force F. Okay, A is being pulled over here. And at the same time, A has a force provided by the bar that is connecting A and B. We already calculated the force. Will be the same magnitude but opposite direction. So this is the T. And this is making a 30-degree angle. Let me just make this nicer here. This is a 30-degree angle here. Right? And A is moving this way. Okay, we'll call this is our positive direction. And remember, A is moving with a 2 meter per second squared. This is our AA. This is given by the question. Therefore, if we do a sum of force, we'll call this x direction then. That's our x positive direction. Sum of fx will be ma a a. Okay, I forgot the b here. MAAA. So looking at the horizontal here, we have a sum of force and the t component be broken into here. So we have 4F minus the force F minus t cos 30 degrees. The horizontal component of the force from the bar at A equals to MAAA. So the force of the piston equals to 2 the mass times 2 the acceleration plus the tension in the bar, 8.21, calculated right from here, cos 30 degrees. Therefore, we can calculate our force is 11.11 Newton. This is our answer. Okay, we calculated the acceleration of B and the force exerting on and the force in the bar at this moment, at this instant. Thank you for watching. I'll see you next time.